you very much. Okay, yeah, got it. So thank you very much. Let me share my screen on my my tablet. Whoops. Can you make me a co-host or something so I can share? Thanks. Screen. Right. So I have a secondary title, which I think is slightly different from what was announced, of Einstein meets Hausdorff, Kantorovich, and Boltmzann. So this is some project, some ongoing projects that I've been involved in for a number of years by now. And there's a version of the talk at the link that you see on my website. Sorry, I'm probably not doing this correctly. Okay, I don't know if this is gonna, I mean, I'm not quite sure, I guess, how can I do this? I can open it in some other thing. Right now, somehow it's open in my email, and so I'm getting this other junk at the bottom that I probably don't necessarily want there, but let's see if I can get rid of it somehow. Okay, reply all, discard changes. Let me try once more. Maybe that's a bit better. Okay, so let me see. So I'm somehow wanting to talk about a non-smooth framework for general relativity. And there are lots of motivations for wanting to do this. One of them is that it's actually radically simpler. So somehow, if you think, general relativity is, of course, a geometrical theory of physics. And Riemannian geometry is fairly hard. You have to learn a lot in order to be a Riemannian geometer. Metric geometry is much simpler because there's somehow, in some sense, it's sparser. So the objects that you have to deal with are more elementary, although in some sense that means you have less structure to work with. So maybe it's harder. And so that's really what we're gunning for, is a kind of metric space theory of general relativity, where you want to replace the smooth manifold by something like a metric space, maybe equipped with a measure. And another reason to want to do this is that, I mean, physically, we know that there are singularities in space-time, like the famous Schwarzschild singularity, and like the Big Bang and the Big Crunch at the beginning and the end of the universe. And so you could wonder whether those singularities are kind of accidents of the fact that we formulated the theory on a smooth manifold. And if you had a kind of singular object, whether you might be able to make predictions beyond singularities or not, or maybe the singularities are fundamental. So there's quite a well-known result in the last few years by Jan Spirsky in the physics literature, showing that even, okay, so the Schwarzschild singularity, you can't get around it in a smooth space-time, but maybe you could get around it in a space-time where the metric tensor only depend continuously instead of smoothly on your location, and he shows that that's not the case. So again, this is going to be another a more flexible generalization of that. And a third reason is that it's nice to be able to take limits of, so for example, you have Riemannian manifolds, but you can approximate lots of non-smooth objects like the cube, for example, with a smooth Riemannian manifolds, even maybe assuming certain kinds of curvature bounds, and you'd like to be able to work on those non-smooth limits. And in some sense, that's also, it's a little bit in the spirit of wanting to complete the rational numbers, and it's more convenient to work with the real numbers. So somehow we'd like to complete the space of Riemannian manifolds or pseudo-Riemannian space-times and deal with some limiting objects. Okay, but anyhow, so the talk today is driven by two sort of famous sign laws in physics. One of them is that gravity is always attractive and never repulsive, and the other one is that entropy always goes up and never down. And so you can wonder, well, of course, one is from the theory of gravity and the other one's from the second law of thermodynamics, and you can wonder whether these might be related, which sounds a bit crazy at first blush, but there's, or maybe hopelessly optimistic at first blush, but there's actually several historical antecedents for connections between gravity and thermodynamics. So almost 50 years ago, Bekenstein discovered what he called the second law of black hole dynamics, which is that when two black holes merge, the area of the horizons can only increase. And about 20 years after that, Ted Jacobson discovered that the Einstein field equations can actually be derived from this, this increase in the surface area of black hole horizons if you assume the second law of thermodynamics and you define the entropy of a black hole to be proportional to its horizon area. And more recently, Eric Verlinde has been pursuing a theory of gravity as an emergent, which is to say a statistical effect. So today I'm going to describe yet another connection between gravity and entropy, maybe not so much thermodynamics, but which is based on optimal transport. And so I have a paper that appeared a couple of years ago about this, and then there was a paper, a preprint that appeared around the same time by Mondino and Schur, and which are sort of the basis for trying to build a non-smooth theory of gravity, which is actually a project that began in work of Michael Kunzinger and Zeeman, which is published even before this, but has been really pushed forward by work of Cavalletti and Mondino, which hopefully will appear, is a preprint from 2 years ago, hopefully will be published soon. And I'm going to describe, depending on how time goes, I'm also going to describe some new work I have in this direction with Clement Zeeman, who spent the last couple of years, most of the pandemic in Toronto as a postdoctoral fellow. Okay. And please don't hesitate to stop me at any time if you have questions to ask. But I realize that this is not a general relativity audience, so I'm going to try to give. It's probably going to be a somewhat impressionistic talk because this is a technical subject, and I'm going to brush as many of the technicalities as I can under the rug. And I am, but I'm also going to give kind of a crash introduction to general relativity as I see it. So of course, before Einstein, there was Newton's theory of gravity, which basically the second law of Newton said that force was mass times acceleration. And if the force was gravitational, then it was proportional to the gravitational mass times the gradient of the potential. And the potential satisfies Poisson's equation and the right-hand side is non-negative. And that's somehow what makes gravity attractive. And of course, there were some observations Newton couldn't explain, and some of them he recognized himself, like that it was sort of a miracle for him that the two masses that appear on these two sides of the equation, in principle, could be different quantities, but they happen to cancel out. And so, in other words, as long as the particle is not too massive, what path it's going to follow doesn't depend on the mass of the particle. And of course, there was the perihelion precession of Mercury. I have the caricature of Galileo's experiment in Pisa, where dropping the two masses and observing that they both hit the bottom at the same time, which was actually very counterintuitive to me when I was a child. I always thought the heavier mass should hit the ground first. I think that maybe because of friction, right? The heavier mass, the force of friction is more, you drop a piece of paper, it takes a long time to fall, but that's not a gravitational effect, it's a friction effect or a feather. So the basic idea of Einstein's theory, and I have to say, I started teaching general relativity about 25 years ago here when I moved to University of Toronto. And what gave me the courage to, I was not a geometer, and what gave me the courage to teach general relativity was reading Kip Thorne's popular book, Black Holes and Time Warps. And I also remember Jim Colliander, my former colleague, complaining a lot about this general relativity course, which he taught some and I taught some, but it was a course that used to have to be offered every year because it was a required course for our mathematical physics majors. And he felt we were wasting our time teaching it, but somehow it wasn't a waste. So here we see teaching inspires research. So for me, it didn't end up being a waste of time because now I'm actually working in the area. Okay, so what's the fundamental idea? The idea is that gravity isn't a force, it's just a manifestation of the curvature of some kind of curvature in the underlying geometry of space-time. And so how could this work? I have this caricature where if you fire two missiles directly south from the equator, they pass pretty close to each other at the South Pole and then again at the North Pole. And if you thought the Earth was flat and not curved, and you plotted the trajectories of the missiles, you might conclude that even though they started out moving parallel, they're attracted to each other, and so they get pulled together, and then inertia carries them past each other, but the attraction pulls them back together. So this is an example of how curvature can manifest itself as a fictitious force. And somehow that's the spirit of the theory of general relativity. Curvature gravity is a fictitious force, which is a manifestation of some kind of underlying curvature. So here's the Einstein field equation. I always get the constant wrong, so hopefully it's 8 pi, but I guess that's mainly a question of units. But basically it's an equation that says, it's an equation for at each point space-time, you have a 4x4 matrix, if it's a 4-dimensional space-time. actually two 4x4 matrices, one of which carries geometric information and the other one carries physical information. And Einstein basically asserts that they're the same matrix. So on the right-hand side, you have what's called the stress energy tensor, which basically measures the flux in the four directions of space-time of the energy and the three components of momentum, the density and the flux of the energy and the momentum. And on the left-hand side, you have an object which is basically, it's almost the Ricci curvature tensor. It's the Ricci curvature tensor minus the multiple of the scalar curvature times the metric. And it happens that you choose the multiple of the scalar curvature that you subtract from the Ricci tensor to make this a divergence-free tensor. And of course, the observations of classical physics are that energy and momentum are conserved, so this tensor is also divergence-free. And once you know that both of these tensors are divergence-free, it's pretty natural to suspect that they might be related or even the same. And Einstein's theory, at least classically, is set in a 3+1 dimensional space-time, which is classically a smooth Lorentzian manifold. But let me, so here is from Kip Thorne's popular book, what I absorbed is the way to think of the Einstein equation and to think of the various curvatures that appear in it are, if you imagine that you're piloting a spaceship and you put it in orbit around a black hole, and you're orbiting the hole with your feet pointing towards it and your head pointing away from it. And if the hole is massive enough and you can adjust your thrusters to put yourself in a lower and lower orbit without crossing the horizon, what you will eventually feel is that your head and feet will start to be stretched away from each other. And at the same time, your front and back, your side to side will be pressed together and your front and back will be pressed together. And that's because your head and your feet are both trying to follow geodesics, straight paths. But in this curved world, the straight paths are trying to diverge from each other. And the ones, your front and back are trying to follow straight curves as well, but the curves are getting closer together, so you feel compressed. And so these forces are what are sometimes called tidal forces, because they're the same forces that make the oceans on the Earth bulge towards and away from the moon. And what the Ricci curvature tensor is, or even the Einstein tensor in this case, we're far from the star, so we're in a vacuum locally. And so the time component of the stress energy is essentially, as long as you and your spacecraft are not very massive, it's essentially zero and not moving too fast. And so the time component of the Einstein tensor in this case is going to be the sum of the x time, y time, and z time components of this Riemann tensor. And by symmetry, your front and back squeezing and your side to side squeezing are going to have the same intensity. And since these things have to add up to zero, that means the force of stretching on your head and feet is twice as strong as the force of compression around your waist. So that's somehow the content of the vacuum Einstein equation in this story. Questions? Right, and so again, classically, this story is set on a four-dimensional Lorentzian manifold, and what it means to be a Lorentzian manifold is that the tangent space at every point, instead of being Euclidean, is a copy of Minkowski space. So in other words, at each point, there is a cone of directions such that tangent vectors inside the cone have, let's say, positive inner product with themselves, and tangent vectors outside the cone have negative inner product with themselves. And tangent vectors along the cone have zero inner product with themselves, and they're called null vectors. These guys are called time-like, and these guys are called space-like, and the guys along the future and past cone are called null vectors. Yeah, so here I'm reiterating some of what I just said, or they're also called light-like if they're tangent to the tangent cone, to the future and past cone. And we're always going to assume that we can make a global choice of orientation on our manifold, so that you can't drag that hourglass around some curve and find that past and future interchange with each other. And a curve on the manifold is said to be time-like, light-like, or space-like if all of its tangent vectors share these same inequalities, and future-directed if it's in the green cone, and past-directed if it's in the red cone. And basically, particles which aren't too heavy in Einstein's theory follow time-like, future-directed curves on the manifold. So the manifold's a collection of events in space-time. And let me also mention the positive energy conditions of Hawking and Penrose, which go back about 50 years, more than 50 years by now. So the so-called weak energy condition asks for the Einstein tensor to be non-negative when you take the inner product of any time-like vector with itself. And that's expected to be satisfied in all physical geometries. There's also a thing called the strong energy condition, which essentially asks that the Ricci tensor have this same non-negativity property for every time-like vector in the space. And the relation between the Ricci tensor and the scalar curvature is basically that the scalar curvature is the trace of the Ricci tensor. It's not as universally satisfied as the weak energy condition, but nevertheless, it played a role in the Hawking, I guess the first singularity theorem, the singularity theorem of Hawking, that said if you're in one of these time-like Ricci non-negative spaces and you can find a submanifold along which the mean curvature is positive, bounded away from zero, and under some additional technical hypotheses, then you can't continue too far into the future of such a space-time. So there'll be some future-directed geodesic which has to end after finite time. So it was a singularity theorem. And that's another reason the presence of these singularity theorems, which say that there are various conditions under which geodesics can't be continued forever, tells you that you would like, it's natural to want to, the smooth description is going to break down at some point, so it'd be nice to have a non-smooth description that hopefully maybe doesn't always break down. Maybe some of the singularities are honest singularities that can't be continued even in the non-smooth theory, but maybe some of the singularities that occur in the smooth theory are just a breakdown of the manifold structure. Okay.
So the strong does not imply weak, right?
Yeah, right. The strong, it's bad nomenclature. But thank you. Yeah. And I'm also, whenever I have a manifold, I'm also going to assume it's globally hyperbolic, which is kind of a completeness assumption. But in particular, what it means is that there's no closed causal curves. You can't go back to the future or forward to the past. And secondly, that whenever you take any two events in the space-time and you look at all the future points of the first event and all the past points of the second event, when you intersect those two things, so you take X and you look at its future, and you take Y and you look at its past, when you intersect those things, you get what's called a causal diamond. And it's a diamond in two-dimensional Minkowski space. It's actually sort of a cone. It's two intersecting cones in three and higher dimensional Minkowski space. You want those to be compact for every pair of points X and Y. Okay, and let me remind you, before I talk about how Lorentzian geometry works, let me remind you how Riemannian geometry works. So when you have by the way, as soon as you have a Lorentzian manifold, there you can always find with these various hypotheses, you can always find a Riemannian metric on it, which is sometimes convenient for having a topology. And I'm going to call the Riemannian metric G tilde when it exists. It's not unique. It's very non-unique, but anyhow. Typically, when you have a positive definite inner product between pairs of tangent vectors, it allows you to assign a notion of length to curves, at least for continuously differentiable or maybe Lipschitz curves. And you get that by integrating maybe the square root of the inner product along the curve. And then you can define a distance, the Riemannian distance between points, so the G tilde distance, would be the infimum among all Lipschitz curve connecting those 2 points of this integral. And as long as the Riemannian manifold is complete, then the inf will be attained. And moreover, you can characterize the curve sigma which attain it by this following property that for every pair of points, here it's convenient that P is strictly larger than 1. For every pair of parameters S and T, the Riemannian distance between sigma of time S and sigma of time T is a fraction T minus S of the distance between the initial and final point. So that's what it means to be a geodesic segment, or on the Riemannian manifold, or a minimizing geodesic. And right. So it looks like D might depend on P, but actually it doesn't, basically because of Jensen's inequality. So people usually take P equals 2, but you can use any P larger than 1. Okay, so there's an analogous story on a Lorentzian manifold. But this time, instead of a parameter larger than 1, I need to take a parameter smaller than 1, which I could have called p, but I chose to call q. And so the idea here is that if you have a pair of events, x and y, on a Lorentzian manifold, you look at all future-directed Lipschitz curves joining them, and you try to maximize instead of minimizing the qth root of the inner product of the tangent vector. And because these are future-directed curves, the inner product is non-negative. And this maximum will be attained if m is globally hyperbolic. And if the so-called Lorentz distance or time separation between the two events x and y is positive, then you can characterize the maximizer in the same way that you did in the Riemannian case by saying that the time. So by the way, this L, it looks like it might depend on Q, but it doesn't, again, because of Jensen's inequality. So this is somehow remarkable that I'm dealing with these exponents less than 1, but because I'm taking a supremum, the Lagrangian here is still concave, and concave supremums are well behaved. So the interpretation of this L is it's the maximum amount that a particle can age when it moves from event x to y. And the question of what, so L is going to be basically positive if x is in the future, time-like future of y. It'll be non-negative if x is in the causal future of y. And I'm going to set it to be minus infinity if y is not in the causal future of x. And I'm also going to make these funny conventions that this Lorentz distance satisfies a kind of backwards triangle inequality because it was defined using a supremum rather than an infimum. And I'm going to make these conventions about what the power of minus infinity should be, which I guess corresponds to choosing a funny branch of the log. But the sense that in which it's the maximum should make you think of the twin paradox. So, which is the paradox where if one twin sort of stays in place and the other twin jets away on a fast rocket and comes back later, the twin that stayed in place will have aged more because the twin that stayed in place followed the geodesic, and the one on the rocket was doing all kinds of accelerating and decelerating. So it's not, the curves are not, it's in Lorentzian geometry, time-like curves are not giving you the shortest age between two events, they're giving you the longest possible age between those events. Okay, so coming back to Riemannian curvature, of course, if you've seen some Riemannian geometry, you've seen the Riemann curvature tensor, but if you haven't seen some Riemannian geometry, here is a way that you can, maybe it's not such a convenient way, but it's at least an easy to interpret way to define it. So take two geodesic segments passing through the same point and look at the distance squared between them as functions. Let's take them to be unit length and arc length parameterized as functions of the parameters s and t. So because Riemannian manifolds are locally Euclidean, what you get at leading order is basically Pythagoras' theorem. And the next order correction to that, you can go all the way up to order 5, and there's only one correction, which is a fourth order correction with 2 copies of s and 2 copies of t. And it turns out to be, so it involves, it's a multilinear object involving 2 copies of the tangent to sigma and 2 copies of the tangent to tau. And that multilinear object is the Riemann curvature tensor, properly normalized. And it's actually, it's a bilinear object in sigma dot wedge tau dot. So it's really, it's the sectional curvature of this 2-dimensional plane spanned by sigma wedge tau dot. And probably if you took a Riemannian geometry course, you would have seen this definition of the Riemann curvature. It also measures the failure of derivatives of vector fields to commute with each other. And its trace gives the Ricci tensor, which is the object that appears in the Einstein field equations. And so miraculously, or not, if you replace d by L and you remove the tildes, you get a similar formula, and you can take that to define the pseudo-Riemannian curvature associated to a Lorentzian metric. And of course, these would need to be now, time-like geodesics. Okay, questions? So I drew a picture. I tried to draw the same picture of the same formula. So here are the tangent vectors, tau dot and sigma dot, and here are the geodesics, the unit length geodesics they generate. And you're measuring this guy here. And by the way, if the Riemannian manifold is positively curved, then the distance between the midpoint of this side and the opposite vertex will be larger than it was in Euclidean space. If it's negatively curved, then this distance would be smaller than in Euclidean space. And so there's a notion of comparing triangles to triangles with the same side lengths in Euclidean space, or maybe a constant curvature space like the sphere or hyperbolic space, which allows you to develop a metric theory of sectional curvatures, as long as you have, which are things associated with triangles or two-dimensional planes, as long as you have geodesics connecting any pair of points in your metric space. And some analogous in a Lorentzian metric space, so in other words, a Lorentzian space equipped with a time separation function, you can do analogous triangle comparisons to define notions of sectional curvature. And this is somehow in smooth setting. This was started by Richard Bishop and Stephanie Alexander, but in the non-smooth setting, it's been developed in this paper 2 years ago by, or 4 years ago by Kunzinger and Zaman. Okay. So gravitational attractivity has something to do with positivity of the Ricci tensor in time-like directions, but so far we haven't seen the entropy or the second law come in. Everything that I'm going to say is now modeled on a theory of metric measure geometry, which is sort of, I'm now working up to the Lorentzian analog of something that's been worked out in the Riemannian case. And in the Riemannian case, there's this long line of developments, which in some sense, was inspired by my thesis and things I did later with Cordero, Rauskin, and Schmuckenschläger, and also Otto and Villani. But it started to crystallize around 2004. So in 2001, what we had shown was that if you're on a Ricci non-negative manifold, then Boltzmann's entropy is going to be convex along certain geodesics and probability measures that are given, the geodesic structure and probability measures given using optimal transportation. And von Resness and Sturm showed the opposite. They showed that unless you have this convexity, the Ricci curvature will not be non-negative. So as soon as non-negativity of the Ricci curvature is violated, this convexity is also violated. And the good news is that convexity of the entropy is something that you can make sense of without a smooth structure. And so this led Sturm and independently Lott and Villani to adopt this entropic convexity along geodesics probability measures as the definition of what it meant to have a lower Ricci bound in a non-smooth metric measure setting. And so you're in a metric space, but you need to make sense of an entropy, and the entropy is defined by using a reference measure. So that's the basic idea of theory. And if you think about classical geometry, to get from the Riemann tensor to the Ricci tensor, you sort of pick a direction and you want to average overall triangles that include that side length, or overall orthogonal directions. In a metric space, you don't know how to do the averaging. And so this measure tells you how to average. And it's undergone dramatic developments in the subsequent 15 years. A lot of them by Ambrosio, Gigli, and Sfari, but also many other authors, and Sturm and his group, his students and collaborators. I'm like way not able to give any kind of comprehensive summary of what's going on in that area. But so some of the different things that it's connected to are contraction results for diffusion semigroups, results like the Bonnet-Myers diameter bound, which was first proven as smooth setting, turn out to work in this metric measure setting as well. That was one of the original applications of the work of Lott, Villani, and Sturm. More recently, there has been an enhancement of this. So let me talk a little bit more about curvature dimension conditions. So what does CDCAN? A metric measure space is CDCAN if its putative dimension is bounded above by n and its putative Ricci curvature is bounded below by k. So in a classical manifold, it would be telling you the dimension is no bigger than capital N and the Ricci curvature is no smaller than capital K. So if you think about even, this includes not only Riemannian manifolds, it includes lots of Finsler manifolds. So even if you think about Euclidean space, but with non-Euclidean norms, like let's say the little LP norms, they all satisfy CD0n, where capital N is bigger than the dimension. But only the Euclidean one satisfies this additional space condition, which is called, somehow came into the theory later through work of Ambrosio, Gigli, and Savary. And Ketterer and Kantorovich recently showed that this extra condition is basically asking that the tangent cone to your metric space at M almost every point be Euclidean. So if your metric space has Euclidean tangent cones at almost every point, then it's not, and it satisfies this entropic curvature dimension condition, then it's actually an RCD-Can space. And under this additional Euclidean tangent space hypothesis, there's a splitting result of Gigli that's opened up many interesting developments. There's also, in some sense, this has been a unifying theory for geometric inequalities. So there's a whole industry of showing things that were known on smooth manifolds under Ricci lower bounds can be extended to non-smooth metric measure spaces. Mondino and Neighbor have given a rectifiability result saying that an RCD-Can space can be covered up to sets of zero measure by, let's say, Lipschitz coordinate charts. So it's not that far from being a manifold, and presumably a lot more is to come. And so what I am hoping to talk about today is, can we do something like this in the Lorentzian instead of the Riemannian setting? Okay, so I still need a topology, so it's convenient to start with a metric space, and I'm gonna assume it's complete and separable. But the fundamental geometry is gonna come from a time separation function, which axiomatically, so Kunzinger and Zeeman have this very axiomatic approach, but I'm gonna make some simplifying hypotheses. I'm always gonna assume that the set where L is non-negative is closed and that L is continuous on that set. And then the additional properties that I need from L are that it satisfies a backwards triangle inequality. It vanishes, the time separation between any point in itself is zero. And if y is in the future of x, so if the time separation from x to y is non-negative, then but y is different from x, then then x cannot be in the future of y. So then that implies L is minus infinity. And once you have such a time separation, you can look at the set where it's non-negative and the set where it's strictly positive, and these both define partial orderings. This one is stricter than that one. And they basically, these partial orderings tell you which events are in the causal or time-like future of each other. And so you say a curve on the manifold's time-like or causal if for every pair of parameter values along the curve, the second point lies in the future of the first point, or either strongly or weakly, strictly or weakly. And all causal curves I'm going to take to be future directed by convention, but of course you could backwards parameterize them and have past directed curves if you needed to do so, but I've never needed to do so. And a metric space equipped with one of these time separation functions is called a Lorentzian geodesic space if whenever y is in the future of x, there is a geodesic joining them, which happens to be Lipschitz for D, but what it means to be geodesic is very analogous to what it meant in the metric space. It means that the age of any subportion of the curve is a fraction t minus s of the age of the full curve. Of course, I need L to be strictly positive because otherwise this doesn't work. I could reparameterize, if L was 0, I could reparameterize, it would still be a geodesic. And again, for convenience, I'm going to assume that my Lorentzian, I guess Kunzinger and Zeeman would call it a Lorentzian pre-length space, but anyhow, I'm going to assume that it's globally hyperbolic and even in some enhanced version, meaning first, there's no closed causal loops, and secondly, that whenever I have a pair of compact subsets in the space, if I look at the future of one of them and intersect it with the past of the other one, I want that guy to be compact. So that's what kappa global hyperbolicity means, and I'm just going to assume it without mentioning hereafter. Okay, and so what we'd like to do is we'd like to build some notion. So as I said, you already have a notion of geodesics. You can already do triangle comparisons, and so you have some notion of sectional curvature bounds at least. Whoops, sorry. I was further than this. I want to work my way towards Ricci curvature bounds, lower bounds anyways. And so it, again, inspired by what the CDKN conditions of Sturm, Lott, and Villani, what we want to do is we want to lift the geometry, which is to say the Lorentz distance. Oh, shoot. Something worse has happened, which is that I have now lost the nib of my pointer. Gosh, I have no idea where it went. It's, I guess it flew off, it dropped off. Let me see if I can point with my finger. No, that's not gonna work. This is very unfortunate. Thanks. Okay. So the idea is to lift the geometry that our time separation endows the space, the set with, I guess the set X. Sorry, I switched back and forth between X and M, and I haven't been systematic. So, so some authors use M when X is a manifold and X otherwise, and I apparently mixed them on my slides, so I apologize for that. So I want to lift the geometry from events to probability measures, to compactly supported probability measures on events. And the way I'm going to do this is using optimal transportation. So when I have a collection of events mu naught, which hopefully lie mostly in the past of a collection of events mu one, I'm going to look at all joint measures on the space cross itself, whose projection onto the first copy of n gives me mu naught, and whose projection onto the second copy of n gives me mu one. So my notation for that is gamma, capital gamma. And I'm going to try to maximize the Qth power of the time separation, the expected Qth power of the time separation. And so what I'll hopefully get is I'll get a correspondence between events here and events there. And of course, as I said, these guys are supposed to be in the future of those guys, so I should turn the picture on its side, but I don't have space on the slide to do that. And this is an optimal transport problem, and it's with respect to an upper semi-continuous, or if you flip the sign, it would be a lower semi-continuous cost. And so the supremum is going to be attained by some gamma, which we'll call LQ maximal or LQ optimal. And now, of course, the cost is behaving a little strangely at the boundary of the set where L is positive. It jumps to minus infinity, but so that complicates life. And in fact, if you were on the smooth manifold, then it would even, its gradient would be blowing up as I approach this set as well, which complicates life. But it's a technical complication for the analysis, but anyhow, it's not a conceptual complication. But this distance depends on a parameter Q. And you could, this is very much analogous to what I would do in the metric space case, where I would be infimizing the expected value of the Pth power of the distance over the same kind of set of measures. And that would define some distance between mu naught and mu one. And then if the underlying space is a geodesic space, then this space here is going to be a geodesic space, and you can construct geodesics connecting these guys. And so this kind of thing was already looked at by Exgen and Muller, and who checked that LQ satisfies a triangle inequality. And again, you can define geodesics for this LQ distance in probability measures. And they always exist, at least provided that you can find a Kantorovich maximizer, an LQ maximizer, for which L is positive almost everywhere, gamma almost everywhere. And for example, one case in which you can do that is when all of the events of mu naught lie in the causal past of all of the events of mu one. And then it's even, you can get nice characterizations of the LQ geodesic that join them. Sorry, again, I'm not systematic on my slides. Sometimes I write LQ geodesic and sometimes I write Q geodesic. And in the smooth setting, at least, if either endpoint is absolutely continuous with respect to the Lorentzian volume, then the curve would be unique. That won't, of course, always be true in the non-smooth setting, but I've given the definition of Lorentzian volume here because it's going to haunt us later on as the talk progresses. But in coordinates, it's basically given by the square root of the determinant of the metric tensor. And when you want to analyze this problem and show things like the uniqueness of this geodesic, and in fact, it also follows, as soon as one of the endpoints is absolutely continuous, it follows that all the interior points are absolutely continuous as well. You need to analyze the maximum that defines LQ. And let me go back to it. Sorry. Here it is. So the thing to notice about this is that, first of all, the set of gammas that I'm varying over is a convex set. It's weak star compact since the measures are compactly supported. And secondly, the thing that I'm trying to maximize, this expected value, is linear in gamma. So really, I'm maximizing a linear function on a convex set, convex compact set. It was not maybe too surprising the supremum is attained. But because I'm maximizing a linear function on a compact convex set, there's also a duality, a dual program from linear programming. And you would expect that this maximum should be equal to a minimum of, you can introduce Lagrange multipliers u and v, which are conjugate to the marginal constraints on the gamma in the maximization problem. And you would expect the mu naught expectation of u plus the mu1 expectation of v, if u plus v dominates the time separation to the qth power, then integrating this against any joint measure gamma with the correct marginals will tell you that this quantity here is going to be larger than this. And in general, you'd expect that equality holds here. And we're going to need to make hypotheses that ensure that equality does hold there. And so there are different ways to do this, but I'm going to follow the nomenclature of the Cavalletti-Mondino preprint. And I'm going to say that a pair of measures are time-like Q-dualizable if this infimum is finite. So in other words, if there exists some measurable integrable u and v that satisfy this inequality. And as soon as that happens, then you get equality here. And secondly, you want at least one Kantorovich maximizing gamma, which puts all of its mass on the time-like future. It has to put all of its mass on the causal future. So this would hold trivially if I put a inequality here, but I want a strict equality. And this time-like Q-dualizability improves to strong time-like Q-dualizability if you can find a subset of the product of the supports living in the positive, the time-like future that contains all the mass of all LQ maximizers. And moreover, which has this funny property which is called being LQ cyclically monotone for the positive part of LQ. And all that means is that whenever I take a finite sequence of points in the set, I can permute the y's with respect to their partners. So I can permute the future events with respect to past events, and the expected time-like separation will only go down. And this is sort of a natural property for S to have if you think that gamma is attaining this maximum over here. So recall that this was max of integral LQ d gamma. And so this, if gamma was a discrete measure, then this would guarantee that I'm doing the max. And if I have it for all sequences of points, then I should expect that characterizes maximality. Okay, so now, as I mentioned earlier, if you want to talk about Ricci bounds, you also need a measure on your space. And so, so I'm just going to fix an arbitrary Radon measure on my complete separable metric space. And but you should have in mind the case where maybe M is not necessarily the Lorentzian volume, but it's proportional to the Lorentzian volume via density, like an exponential density. So of course, the proportionality coefficient should be non-negative, so it's convenient to write it as an exponential. And then whatever measure you've chosen, I'm going to look at the entropy relative to that measure, which is basically if I take an arbitrary probability measure with compact support, and it happens to be absolutely continuous with respect to the reference measure, then I look at its rho log rho entropy. And if it's not absolutely continuous, I define the entropy to be plus infinity. And notice that my entropy I've defined with the opposite convention to the physics literature. So when things are more spread out in my story and things are more uncertain, my entropy would be smaller, whereas the physicist's entropy would be larger. This L log L entropy is like a limit of an LP norm when P is bigger than 1. And so LP norms go down when things are spread out for probability measures anyways. And so here comes somehow the crucial definition of the talk. I'm sorry, it's a little late in coming. So you fix a pair of parameters K and N, and then you write that this metric measure space with this time separation function L is has weakly time-like curvature dimension parameters K and N. If and only if, whenever you look at a finite pair of probability measures that are strongly Q-dualizable, then you can find an LQ maximizer inducing an LQ geodesic joining them, along which the entropy is convex if k is non-negative. So its distributional second derivative should satisfy this lower bound. And because this is a semi-convexity bound, it tells me that the E is always locally Lipschitz, and so I can make sense of its first derivative squared. And notice that the bigger n is, the easier this is to satisfy, and the smaller k is, the easier this is to satisfy. And so this somehow, this weak time-like curvature dimension condition is asking my dimension of my space to be bounded above by n and its Ricci curvature to be bounded below by k. And so the definition that I wrote was actually formulated by Cavaletti and Mondino. And they go on to prove that, first of all, the set of such spaces is closed in a natural topology. And so it provides a framework in which you can take limits of the Lorentzian manifolds and get possibly not singular objects emerging, but still that you can still handle in some way. And they are able to show things like the Hawking singularity theorem generalizes to this setting. And somehow at the same time, I was working with Annegret Bircher and Kristen Ketterer and Eric Woolger on a kind of Riemannian analog of the Hawking singularity theorem. So in the Riemannian setting, we're able to go a little further and characterize Hawking tells you that you can't go too far into the future before you hit a singularity. The Riemannian analog tells you if you're in a, let's say, Ricci non-negative space, and you have measure space, and you have with finite n, and you have you find a set in it whose boundary is, in a certain sense, has a positive lower bound on its mean curvature, then you can't fit too big a ball in that set, and we're able to say how big the ball can be and which sets attain equality. So we can go a little further, at least in the RCD-KN setting. And anyhow, here is the theorem which motivates the definition, and this was a theorem that I proved actually before the definition was formulated. So if I fix a set of parameters, and I'm dealing with a globally hyperbolic smooth space-time, and I take a reference measure proportional to its volume, then it's going to satisfy this weak time-like curvature dimension condition with parameters k and n, if and only if one of two things happen. Either the topological dimension is the putative dimension, capital N, in which case V has to be constant, and the ordinary Ricci curvature has a lower bound in all time-like directions. So if you took k to be 0, that would be the Hawking-Penrose strong energy condition. Or the topological dimension is smaller than the putative dimension, and then you have to look at this funny thing, which is called the Bakriami-Ricci tensor, which says you modify the Ricci tensor by adding the Hessian of V and subtracting this rank 1 object with a coefficient which would blow up if capital N was equal to little n. And it's that object which has to be non-negative in all unit time-like directions. And as I said, at the same time I was doing this, shortly after I did this, a preprint came out by Mondino and Sur, in which they were able to go a little further and say not only when do lower bounds hold, but they were able to show how you can use entropic convexity to characterize when equality holds here. So in some sense, they're able to give upper bounds as well, in a sense to the Einstein field equation in a metric measure setting equipped with a time separation. But the upper bounds are unstable, whereas the lower bounds are stable. Okay. And I'm almost out of time. I have a couple of pictures which give the intuition behind this theorem. So the intuition is I paired these events. This is borrowed from Villani's book, which is inspired by my thesis. I pair the events in the past with the events in the future. I construct this LQ geodesic between them. If things are more spread out in the middle, then I'm Ricci positive, like they would be on the sphere. If they're less spread out in the middle, so if things focus in a saddle or something, then the L log L norm is going to be bigger in the middle, then I'm not Ricci positive. Okay, so I've got a couple more minutes. So a central role in the theory of metric spaces is played by the Hausdorff dimension and measure. And I have recalled the definition for you. So when A is a subset of a metric space, then you look at coverings of A by subsets of small diameter, delta, and you add up the nth power of the diameters of the AI, and you try to minimize that quantity. And there's some normalization constant in front that doesn't matter much. But so these objects, they're not measures, they're outer measures, but they're monotone in delta, and the limit as delta goes to 0 is indeed a Borel measure. And you can define the Hausdorff dimension of a set. So there's a sharp transition. There's a smallest n for which the n-dimensional Hausdorff measure is 0, and a largest n for which it's infinity, and that the infant soup agree and define the dimension. And they play kind of a central role in the CD-KN theory. So for example, Kolding and Cheeger 30 years ago, when they were looking at limits of Ricci manifolds, identified a dichotomy between what they called non-collapsed limits and collapsed limits. And it had to do with whether or not you look at the volume of the unit ball along a sequence, and either the volume is going to zero or it's not. If it's not going to zero, then the limiting measure is going to be a multiple of the Hausdorff measure of dimension, the topological dimension capital N. And so in these better spaces last year, Brew and Simola were able to show that whenever you have one of these Riemannian curvature dimension spaces with curvature parameters k and n, I think n has to be finite here, then there's an integer such that most of the points are regular. So you can throw away a set of measure 0 such that the restriction of the measure to that set is absolutely continuous with respect to Hausdorff measure of whatever of that integer dimension k. So that this is already suggesting these are looking a bit like manifolds of a particular dimension. So what Simon and I have done in this preprint is we've tried to figure out what the analog in the Lorentzian length space setting of, or Lorentzian geodesic space setting of Hausdorff dimension is. So we'd like to build a notion of measure and dimension around L instead of D. And I'm a little bit over time, but I'm also on my last couple of slides. So can I have a couple of extra minutes? Okay. So so the idea is you don't have balls anymore, but you can look at causal diamonds. So you can take points A and B and look at their intersection, and you can try and cover an arbitrary. So by the way, if I had insisted that my sets AI be balls here, I would have gotten something that differed from the Hausdorff measure by constants above and below, something called the spherical Hausdorff measure that differs from the usual one by constants above and below. So the dimension is invariant. So here what we're going to do is we're going to look at coverings of A by unions of these causal diamonds. And we're going to take the B will always be in the future of A, and then we're going to raise the time elapsed between A and B to the nth power and take a minimum. And this time the normalization constant has to do with the geometry of cones instead of the geometry of spheres. But anyways, again, the limit, this is monotone in delta and the limits of Borel measure. And we're able to, again, under some mild hypothesis, which I have on the next slide, namely that locally uniformly L should go to 0 as D goes to 0, there will be a sharp transition which allows us to define a geometric dimension. We call it the L dimension of A, or the Lorentzian dimension of A. And this looks like these definitions look like they depend on the diameter here depends on D, but it's very mild. So if you look at two metrics that stay within a bounded ratio of each other, then the Lorentzian volume of dimension n that we're defining here won't depend on which distance function you chose, but it depends very sensitively on L. And already in Minkowski space, this geometric dimension that we define, so if you look at algebraic subspaces of Euclidean space with the Minkowski metric, with the signature 1 metric, there are subspaces where the restriction of the metric is Euclidean. There are others where it's Lorentzian, and then there are some where the metric degenerates and it's null. And so if you look at a subspace where the restriction of the metric is Euclidean, then the Hausdorff dimension and the Lorentzian dimension of that subspace agree. But if you look at one where the metric degenerates and the Hausdorff measure and the Lorentzian measure are positive multiples of each other. But if you look at an algebraic subspace where the metric degenerates, then the Lorentzian dimension is going to be 1 less than the Hausdorff dimension. The non-trivial Lorentzian volume is going to be basically the tensor product of counting measure with the non-trivial Hausdorff measure of that volume. And we also, it's natural to expect that if your Lorentzian length space has this, satisfies one of these curvature dimension conditions, then at least by analogy with what happens in the CDN case, it's natural to expect that the geometric dimension should be dominated by the parameter n. We weren't able to prove this in generality, but we were able to show this for a class of spacetimes that are of some physical interest, namely those spacetimes where the metric tensor is not smooth, but depends continuously on the point as you move around, so that the exponential map is multi-valued, so you can have a tangent vector, it might have more than one exponential, because you don't have a Cauchy-Lipschitz theorem. You still have existence of solutions to ODEs, but not uniqueness. So time-like branching can occur. So you can have two geodesics going along together for a while and then splitting up and doing something different in such a space. And we're able to show in such a space, if you have this lower bound on your Ricci dimension, upper bound on your putative dimension, then the geometric dimension we define is no bigger than n plus 1. We expect it should be n, and we more or less know what would be involved in getting it down to n, but a cheap way of getting it down to n is to just assume if we just rule out time-like branching, then you actually get the expected bound. So my time is up. I have a slide of conclusions that maybe I'll put up. But what are the conclusions? So basically, when you look at the fractional powers of the time separation, then the maximization problem which defines geodesics actually comes from a smooth, strictly convex Lagrangian and away from the light cone. But the singularities along the light cone complicate the analysis. And optimal transport with respect to that cost allows you to lift the geometry from events to probability measures. And this lifting becomes analytically tractable when you make these restrictions on the initial and final probability measures. And we're able to show that the convexity properties of Boltzmann's entropy along time-like geodesics probability measures provides a robust reformulation of the strong energy condition that you can make sense of, not only in the smooth manifold setting, but also in a non-smooth metric measure space setting. And so this kind of gives a new approach to gravity without smoothness. And whereas the second law of thermodynamics is encoded in the first time derivative of the entropy, the Einstein equations of gravity are somehow encoded in the second time derivative of the entropy along these LQ geodesics. Thank you very much, and sorry for going over time today.